Hello everyone, and welcome to the AI Research Roundup. I am your host, Alex. Today we're kicking things off with a paper from May 16th, 2025, called PoE-World, which is short for Compositional World Modeling with Products of Programmatic Experts. The central challenge this paper tackles is teaching an AI how the world works. Traditional methods need massive amounts of data. This paper proposes a different approach using what's called program synthesis, where an LLM automatically writes a world model as source code. It builds this model by combining many small, specialized programs or experts, which allows it to learn complex rules from very little data. And if you want to dive deeper, the authors have released all the code for this work. The repository has the full implementation, including the agent and learner modules. You'll also find instructions to run their method on Atari games like Pong and Montezuma's Revenge. A key part of the agent's planning is an algorithm called Monte Carlo Tree Search, or MCTS, which helps it decide on the best moves by simulating many possible future outcomes. Alright, so this first figure gives a great visual overview of the whole PoE-World process. On the top left, in panel A, we see the core idea. The world model is a combination of many small, weighted expert programs. Think of these as simple if-then rules, like if the player touches a ladder, their velocity changes. Panel B shows how these experts are learned. The system watches a short gameplay demo, and an LLM generates the initial code for these rules. Then, the system refines the model by learning how important each rule is. Finally, panels C and D show the payoff. The agent uses this model to plan, imagining the results of different actions. And because the rules are general, the agent can apply its model to completely new levels of a game, like in Montezuma's Revenge, and still know how to play. Okay, so this next figure zooms in on exactly how those simple expert programs work together. On the right, you can see 3 little Python programs. For example, 2 of them are about what happens when the player is on a platform and moves right. They just disagree slightly on the exact speed. Each of these programs is interpreted as a probability distribution, which is just a way of representing a range of possible outcomes. Each expert also has a weight, which you can think of as its influence. The model then combines these weighted experts to form a final prediction, shown here as a heat map, where the darkest red area is the most likely spot the player will be in the next moment. So, to really test how well this PoE-World model works, the researchers didn't just use the standard Atari games. They created these alternative versions, which you can see here. On the left is Pong-Alt. Instead of 1 ball and 1 opponent, the agent has to hit 3 separate balls past 3 enemy paddles. And on the right, we have Montezuma's Revenge Alt, where the goal is to navigate past moving skulls and climb ladders to grab a key. Using these modified games is a great way to check if the model truly understands the rules and can adapt. And these charts show the payoff. They plot the maximum score achieved versus the number of training steps. Our method, PoE-World, is the dashed blue line. Now, compare it to PPO, the solid purple line. PPO, or Proximal Policy Optimization, is a powerful standard method that learns from massive trial and error. In the Pong games, PPO eventually surpasses PoE-World, but it takes over 1 million steps to do so. The most striking result is in Montezuma's Revenge, where only PoE-World scores anything at all. The other methods are completely stuck at 0. Okay, and this table really drives that point home with the exact numbers. We're looking at the final scores for each method across the 4 games. You can see several baselines, including one called LLM as agent, which uses a technique called React, where the model tries to reason its way through the game. In Pong, our plus planner method scores around -12, which is significantly better than those other low data methods. But the really stunning result is in Montezuma's Revenge, where PoE-World gets a perfect score of 100, while every single other method scores 0. So, we've seen how PoE-World can be used directly for planning, but it turns out it can also give other powerful methods a boost. This chart shows that benefit for the game Pong. The red line is a standard agent using proximal policy optimization, learning from scratch. The blue line is the same agent, but it was first pre-trained using our PoE-World model. Essentially, it got to practice in our simulated world before playing the real game. You can see the blue line is consistently higher, especially early on. This pre-training gives the agent a clear head start, helping it learn faster. Alright, so we saw that the planner is key, especially in Montezuma's Revenge. This table shows a really interesting detail about how that planner succeeds. It compares the model with and without something called hard constraints. These are additional rules that prevent the model from considering physically impossible futures, like the player walking straight through a wall. You can see in the planning successes column, adding these constraints more than doubles the success rate, from 2 out of 9 tries to 5 out of 9. But what's fascinating is that the accuracy for predicting just the next single frame barely changes. This result shows that these hard constraints are absolutely vital for successful long-term planning. It really seems that for complex planning, understanding the rules of the world is just as important as predicting the next frame. The PoE-World paper shows a powerful way forward. By building a world model from specialized, compositional parts, it can learn game dynamics with very little data. This structured approach is what allows it to solve famously hard games like Montezuma's Revenge. It's a fascinating step toward more robust and data-efficient AI agents. Well, that's all we have for today. Thanks for tuning in to the AI Research Roundup. I'm Alex.